All right, so where we're headed in the class at this point, there are two, I think I showed this on Tuesday before the test, two fundamental problems that calculus addresses. And so this is, you know how much of something you have and you want to know at what rate it's changing at any point in time, and vice versa. If you know what rate something's changing at any point in time, you should be able to determine how much of it you have, or use one to find the other. Sometimes you need additional information like how much of something I have overall would depend on how much I started with also. But in any case, we've mostly discussed this bottom one. We just have a few small details of making it exact instead of approximate yet to talk about. So it kind of maybe seems like a strange place to break and take a test. But the situation with this is we can do this bottom one, we can take these rates, make approximate rate functions, and estimate accumulation due to those rates. And we can make better and better estimates. But the notation that we're going to use is kind of, well, we can write it as exact, but it doesn't give us any additional tools at that point. So what we're going to do, starting on maybe the end of class today, maybe Thursday, is start thinking about the other way around, because the algebra of how to work these problems the other way around is actually easier, although it doesn't make any sense unless we've done the first half. So we're going to kind of go back and forth a little bit until we can meet in the middle and go around and around, back and forth from rates to accumulations, symbolically, as well as algebraically, like being able to compute things. Because at this point we can write these expressions, but we can't actually compute anything or write a nice formula. We can write these ugly sums, and that's about where we're stuck at this point. But we're going to fix that. So in any case, this how much of a quantity you have, wanting to know how fast it's changing or at what rate it's changing, doesn't have to be fast like at a rate with respect to time, that's called differential calculus. The part that we've been working on is called integral calculus. Integral as in integrating, putting everything together. So I find a rate from a first interval, find what happens due to that, add it to the rate from the second interval, and what happens due to that, and adding up all the pieces, integrating them together to have some one lump sum, an integral, is what we're going to call this one lump sum when we make it exact. Differential calculus is exactly the reverse. And so you can think of just like integrating and differentiating our reverse words in English, like antonyms, if you want to be English major about it or something. But putting everything together versus separating it out and finding all the different pieces, there are two reverse processes that we're going to use. But what we've worked on so far, and I think I even showed this if I remember correctly. So if we have an exact rate of change function, and I want to generate, although we haven't been able to do so quite yet, an exact accumulation function, we started by estimating, and when we're drawing it out, a poor estimate maybe, imagining small intervals of time, small moments of our independent variable, and using that rate for a little bit, and then using another constant rate for a next interval, and so on and so on and so on. And we called that function r sub f would be the exact, and r would be the approximate. So these little blue lines we called just r without the subscript, but we can also call it, if I wanted to graph this from left to right, be r sub f of left of x. I'd have to define my intervals and starting point, but left of x tells you the x value at the beginning of an interval. And we're going to use that for every interval. So as x grows, I go from using the rate value at the start of this first interval to the rate value at the start of the second interval, and so on and so on. So then to get accumulation, we started by having these like piecewise linear kind of connect the dots sort of looking graphs with jagged lines. When we had relatively large intervals, it was a not great approximation, but considering how bad an approximation these blue lines are for this rate, that's actually not too bad. It's fairly close to this idea of some exact accumulation. The example that we talked about before your test that this picture came from, it was pouring sand onto a scale at a rate in hundreds of pounds per minute. So I have hundreds of pounds per minute for a while that went up to as far as almost 500 pounds per minute and then back down again. So the amount of sand on the scale at first grew slowly or increased slowly, and then more quickly, most quickly in the center section, we're using a rate of about 500 pounds per minute or second, I forget what the time units were. and then it slowed down again, a lower but positive rate means that although my accumulation of sand continued to increase, it increased more and more slowly as we went on. But the idea was, if we make these intervals that we're using smaller, the approximation to the rate will be better, so the approximation to the accumulation will be better. And if we make them smaller and smaller, we can eventually get something that's indistinguishable from a nice smooth curve. It just kind of centers in or hones in on one particular section. So this is just kind of some, at this point, magical, yeah, I can imagine this happening, but we haven't actually talked about the mathematics of it. Just make the intervals smaller and it'll, well, it can't be too lumpy anymore, just trying to draw like little tiny line segments connected to one another. The steepness of one versus the steepness of the next can't have changed too much because the little rate estimates that we're using are so close together. So we call this, if we can go directly from one to the other without passing through all those other steps, just in terms of how to write what we want to do. And the way that we write this is called using an integral formation. And I'm going to write using an integral how to express using a rate that's called R sub f and generating exact net accumulation, A sub f, from that. So with the subscripts, these are representative of exact as opposed to approximate functions. And where this comes from is imagining that that delta x approaches 0. It gets smaller and smaller, infinitesimally small. So the symbols that we're going to use look like this. So here's how I can write out. Now again, this doesn't tell me how to get any values. It's just an expression, much like the sum was, only there's a lot fewer pieces. This expression here represents the exact accumulation by point x as an independent variable for any value of x, where instead of having a sum, I'm going to kind of compare this on the next slide to our summation that we dealt with, where I'm summing up what this symbol is called an integral sign, but it's a stylized Germanic S is what it came from. So you can imagine S for sum. I'm summing from a to x. Instead of counting how many intervals I have, I'm just talking about where I'm summing from visually from left to right, instead of counting interval 1, interval 2, interval 3, because if you can imagine them being infinitely small, there's going to be infinitely many of them. But I'm using this rate function times a little bit of change in my independent variable, but my rate function is evaluated at, and there's this mystery t that's appeared. T somewhat plays the same role as j does. It tells us where we are between a and x, but we use it as a variable. We just let t take on all the values from a to x. So it's kind of the same as letting j take on all the values from 1 through that floor notation in our summation. It's kind of the same idea as that. It's not quite the same, but it's the same idea as that. I'm going to evaluate my rate function at all the spots between a and x for any value of x, and take my rate times, instead of delta t, it's infinitely small. I'm imagining I'm calling this a dt now. So here's the kind of matchup between the parts, or where this came from, how this notation really represents the same thing. It's not an exact one-to-one, like this letter means the same as that in the sum. There's very similar pieces, and you'll see this is this mdx sort of formation. But our approximate net accumulation function was this whole ugly thing, where we had intervals numbered 1 through some number up here, x minus a over delta x, rounded down to a whole number. So we had some whole number of intervals, and we evaluated the rate function at the beginning of each of them and multiplied by the length of those intervals. So as an mdx, we added up all of those different mdx's, all those different amounts of accumulation, change in y, the dependent variable, due to all these different rates. And then this one stray term that doesn't quite fit in the sum is really the same formation. It's a rate times the length of time for which we use the rate. It's just that, well, if we're not all the way through an interval, I don't want to multiply by the length of the interval. I just want to multiply by how far I am into the interval. So this is for our current or incomplete interval. And these are for all the completed intervals that x has already passed. And so as x increases, this becomes larger and larger a sum, not necessarily in its value, because it could have positives and negatives, but it's more and more pieces added together as x increases. And this is always just one stray term at the end, which could have a value of 0 if your x value is right at a boundary of intervals. So in comparison to the exact net accumulation function, again, like I said, this top one, I start with interval number 1 through interval number whatever that works out to be. It gives us a whole number though, and j taking on all the different values gives us all the different input values, x values, to use in our exact rate function. In this case, what I'm going to do is use t, just something. It's kind of like this j. It's not something that I'm graphing. It's just something I'm imagining, taking on all the values from a through x. So it starts at a and goes through x, whatever x might be. As x gets larger and larger, I add up more and more pieces. This still represents sum, but it represents a sum where there's essentially infinitely many components to the sum. So to read it out loud, if you want to read the integral symbol below, you can say it in mathematics language, which is the integral from a to x of r sub f of t times dt. But that doesn't really mean anything. What this tells us, though, is this exact accumulation is found by summing up all of the changes in our function at the rate of change, r sub f of t, at every moment between a and x. Or we're finding the accumulation due to exact rates, all the rates between time a and time x if it's a time, or value a and value x in general if it's something else. You could translate it into a specific context. But a sub f of x is the accumulation of changes in f. Now f is this mystery other function, the total amount where I'd need to know, well, where did you start from in order to actually get that value. But changes in f due to its changing at the rate r sub f of t at every moment t in the interval a through x. So t is just something that I let take on all the values from the beginning to the end of the interval in question. If x is a specific number, like a is going to be, it's like if it's from 1 through 7, that I let t take on all the values, all infinitely many real values between 1 and 7. And I use all of those. So this isn't something, like I can write it, but it still doesn't give me a way to compute things. That's what I want to get at. It gives us, this is the way that we want to write something to indicate that we're doing an exact amount of accumulation. Although, and especially compared to the approximate, it doesn't give us a way to get a nice value by the time we're done. So thinking about the sand and the scale, what I said about this function f, this mystery other function that depends on how much we started with. So this is a net accumulation function. Net accumulation is just the change that happened between time a and something else due to the rate function. It doesn't tell us how much we started with of whatever it was, whether it's driving and I want to measure how far I've driven, where I am, but where did I start? Or if I want to talk about the sand question here, this exact accumulation function of this form, all I could do is pop in the sand formula for rate right there, would tell me how much new sand was poured onto the scale since time A. But if I want to know how much is on the scale at any point in time, then I want to have that initial value plus all of the changes. So it's that y initial plus the sum of all the MDXs. So if the scale already had P 100 pounds of sands on it, it was measured in hundreds of pounds per minute or second, whatever it was, then all I have to do is, well, this is a new accumulation. All I need is y initial plus that, so P plus what happens due to the rate. And you can do this for any value of a, in this case time. So whatever time we start at, if I know the amount, the total amount that I have at a point in time and the rate function at any point in time after that, I can write the total amount, not just the new accumulation, by taking that initial value plus everything that happens due to my rate. So this integral symbol here is just everything that happens due to the rate. This is taking all of the infinitely many different rate values and multiplying them by a little tiny bit of time. In the case of this one, it was pouring sand onto the scale for a while. So this gives us a way to write it. It doesn't solve all of our problems, but this gives us a way to write exact accumulation, this A sub f, and exact total amount by only knowing a rate in the case of the accumulation and a rate with an initial value for the total amount or the total accumulation function. So just the kind of point-by-point comparison here. And it's not exactly the same, but they represent the same pieces mathematically. So here's the exact accumulation at the top, A sub f of x, versus approximate accumulation, A of x, without the subscript. And so that rule on the right, you can see this is much nicer to write. It doesn't really tell us everything that's going on, but it's much nicer to write. And it means the same as this when we have an infinitesimally small value of delta x. When delta x is infinitesimally small, you can maybe imagine this delta x versus x minus left of x. They can't really be different in size, because how can I be part of the way through an interval that's infinitesimally small? If you make it small enough, whenever you've moved, you're into the next interval, if you want to imagine that. So this current term kind of drops out of being necessary to have. If I've gone up through any point in time, I can think of being done with however many infinitesimally small intervals. So the accumulation in each completed interval and the accumulation in the current interval, they both happen for the same amount of time, essentially, that dx and delta x essentially become the same. So let's just put that in there. Say, all right, we don't need this one extra term because they're all essentially the same length. Now, in terms of counting, well, how do I count them when it's infinitely small? With difficulty, which is why we get a new notation. But just the pieces in this, thinking about all the parts that we've said. So we know how fast something is changing, and we want to know all that stuff that was on the board at the start of class today. We want to know how fast something's changing, or we know how fast something's changing. We want to know how much we have. Well, if we know how fast something's changing, that's like the we know a rate function. The rate function's in both of these. Approximate down below, exact up above. And we want to know how much of something we have. Well, it's like that's the answer to either of these, approximate or exact accumulation. So symbol-wise, those two mean exactly the same part of that sentence. So we find this by summing up little bits of accumulation. So when we did approximate, we used that Greek sigma, which is a Greek S. When we did the exact, we changed our Germanic S in honor of the Austro-German sorts of people who are working on calculus. So Leibniz and I guess Newton was working on some of it also, but there are calculus textbooks that were written by a lot of people in what's now present day Austria, Germany, kind of Central Europe. So we get the Germanic S to go along with that. So many bits of accumulation. So for adding up accumulation, that's adding up the MDXs. So we have rates times a little bit of change in our independent variable. So in our sum, that was our rate function evaluated at the left end of an interval times the length of an interval. In our integral expression, it's just the rate evaluated at some t that's in our overall interval of interest times dt, and thinking of that as a very small change in our independent variable, or letting t vary by a little bit between a and x, and use that rate for just a little bit, a moment. So the starting value of x, that a, where we're measuring accumulation relative to, that's represented in both. In the summation, it was a bit messier. How do I include this? And it showed up both in this upper limit of the sum and also here in the rate, so that my first place where I evaluated the rate was r of a, because subbing in j equals 1 makes the rest of this go as 0. So we started at a to the current value of x. Current value of x is just x, which in the sum was just indicated here, also in the current term, which we have since eliminated, but it's the same sort of thing. It's the beginning of the interval that we're in. This is indicating, in this spot, it was actually helping us count how many intervals we had to go through, but it does show up in both of these exact and approximate accumulation formulas. And in terms of all of these, so that's that whole sentence. We know how fast something's changing. We want to know how much of it we have, and we do that by summing up many bits of change over different intervals. So over one whole interval from A to wherever, A to X, using all of the different rates in between versus using a lot of different rates in between. That's the difference between exact and approximate. So the independent variable in both of these functions, question number 7 here, I guess, the independent variable of each function, you can see in the function notation, right, is that x. Okay? So that independent variable, accumulation through x, starting at lowercase a, or accumulation in an exact form between a and x. So independent variable, though, is x in both of these, and maybe it's a point in time, maybe it's something else, but whatever that x is, it shows up in the function notation and also as the where you stop accumulation. So it's accumulation up to a certain independent variable value. The dependent variables, function notation, whole thing, a sub f of x or a of x, that's like our overall total change in y. Oop, I didn't mean to click that. Sorry. Didn't mean to skip all the way through that. But I did want to point out just the dependent variable is the total amount of accumulation between time a and x. It's not how much of something I have all on its own, because neither of these represent a starting value. They just tell us what happened due to a rate, not any other things that might have contributed, such as like how much money do you have in your bank account? Have you been earning money at a rate of X number of dollars per day? Well, how much did you start with? Did you start at 0 or did you start at something else? So looking at these possibly weird looking structures here, some of these are all of these are expressions using an integral sign. Some of them could represent what we were just talking about. Some of them could represent an amount of accumulation due to a rate that's shown being used over a specific interval. And some of them have more variables, some of them have fewer variables and more other sorts of expressions. But this is something that I'm going to post for you to think about tonight. I just want to talk about maybe a couple of these directly right now. But for instance, if I want to figure out if something's a valid accumulation function, it needs to have the pieces that we were just looking at. So some of these are possibly functions. Some of them are just at some sort of numerical value, and some of them are nonsense. Like there's letters in the wrong places, and it doesn't actually mean what it was maybe trying to mean. So for instance, this first question here, this looks pretty much like, other than as a G instead of an R, it looks pretty much like what we were just looking at on the previous page. So if I want to describe what this does, if this is an accumulation function, this would measure accumulation starting at 4 up through x, using a rate given by function g, and I let t take on all the values between 4 and x. So this would be an example of what's a good, valid accumulation function, meaning I can put together all the pieces. I'm going to substitute in, you can imagine substituting in all the values, infinitely many of them, from 4 to any value of x in place of this t, and then let t vary by a little bit before you pick the next one. And then add up all of those mdx's. That's what this does. And since it ends at a variable point x, this is a function. It's not a specific numerical value. On the other hand, this cosine expression over here has different letters. It has x's instead of t's, but notice if this is a rate function here, and that's fine, if this is a rate function, I let x take on all the values between 0 and 8, and then I let x vary by a little bit before I pick the next value. So I'm picking infinitely many values between 0 and 8 and adding up all those mdx's. By the time I'm done, I don't actually have a function. I have a numerical value. This is like, if it was a sand question, this would be the equivalent of write an expression for how much sand was poured onto the scale between time 0 and time 8. So this cosine expression here is an example of not a function, but a numerical value that could validly be interpreted as maybe this is a rate of change of something, and it happens over the interval 0 through 8. But this would give me a numerical result. This is something you could type into GC, and it would actually tell you a value for it that's just a number. I might be able to do that. Let's see. Cosine of x plus x cubed. So let me pull up GC. Ooh, we'll be doing that later. So under this math expression here, there's a bunch of things. One of them is integral. And by default, it gives you 0 through 1, but let's fill in the blank. You can put in whatever you want. I'm going to do 0 through 8. And cosine of x dx, it also automatically, I'm pointing at my screen, also automatically gives you a dx at the end. You can't change that to a different variable, so just use x's as needed. But you can see this has a value to it. Now it was actually cosine of something else. I forget what it was. Cosine of x cubed plus something, or cosine of x plus x cubed. All right. Plus x cubed. Oops, there we go. So this has this particular value. Now, what does that mean? Well, if this was the rate at which sand was being poured onto a scale, then this would be how much sand was poured onto the scale between time 0 and 8, whatever the units might be. It was in hundreds of pounds per second in our example. It might not make sense for this. But this is the total accumulation over this interval. It's a numerical value. So back to what we're looking at here. This first one is an accumulation function because I let g cause accumulation from time 4 to any time x. So there isn't like a numerical aspect to the end. It's like, oh, plug in an x and then I could find out for any value of x, I could find out how much accumulated. It would still be a formula sort of thing. This one is a numerical sort of expression. And let me just point out this one here. R sub h of x dx. So I've got something that's just function notation here. But okay, so let's say that this is an exact accumulation function. It tells me how h changes. This is the rate of change function for a function h. And I let it accumulate from -3 through x. That all sounds fine. The only thing is that x is used in 2 spots here. And it can't have the same meaning in both spots. So if I let x vary from -3 to x, well, that sounds a little weird. But if you can imagine, this first question here, I let t vary from 4 through x. And supposedly there's some sort of, I could graph this if I had an actual function for g. I could let g vary, or x vary from 4, or t vary from 4 through x. Sorry, let me say the letters in the right places. So if I wanted to find the accumulation by time 17, I put in 17 for x, and I let t vary from 4 through 17. If I try to do that with this guy, say, oh, well, if this is an accumulation function, let me find the accumulation by time 5. So I sub in x equals 5, and then I use all the rates from -3 through 5, r sub h of 5, because that's also an x. If I'm substituting in a value for x, I have to do it in all the places. So what would happen is, although it looks like an accumulation function, it would actually be using a single rate the whole time. It'd be using the exact rate at 5 if I want to find the accumulation through 5, and that's not generally how we do these things. So that's why we generally use 2 different letters, one inside the integral, in the integrand is what it's called. And sometimes this letter in here is called a dummy variable. It's not meaningless, it's just that it's not something that came from the problem, just kind of like the j with our summation. It helps us evaluate the expression. It's not something that ends up there by the time we're done if we evaluate it. But we let t take on all the values from 4 to x for any x. If I let x take on all the values from -3 to x, then I can't assign a value to x because I have to let it vary and I can't give it a value. So this top right one has an issue with too many x's in different places. This left one is an accumulation function, and this cosine thing is an amount of accumulation. It's the accumulation from 0 to 8. So those are 3 different things. So I'm going to post this whole list of 6, but we've talked about 3 of them. Take a look at the remaining 3 and see if you can figure out if any of those represent valid accumulation functions or what they are or aren't if they're not an accumulation function. All right, so I want to take a look at just this picture here. So it says a tub has a clogged drain and still lets some water through. We talked about how to sink those clogged also because there's lots of clogged plumbing. But at t equals 0 minutes, the faucet's turned on. And the following graph shows the rate of change of the volume of water in the tub in gallons per minute as a function of time. So we've looked at rate functions like this for a while now. But what I wanted to indicate about this or focus on is the fact that this rate has some positive values and some negative values. So there's 2 different things going on here. So think about what this rate graph means about the amount of water in the tub or how the water in the tub is changing in volume. And there are a few questions down below. I'll read them. I know it's a little bit small maybe in the back. But part A says, at what time does the tub have the most water in it? Explain your reasoning. These tick marks here are 1. So this is 1 minute, 2 minutes, 3 minutes, 4 minutes, 5 minutes, 6 minutes. The last one indicated as 7. So at what time does the tub have the most water? At what time does it have the least water? And part C is there more or less water in the tub at time 7 than when the faucet was first turned on? That would be at time 0. And so think about that. Maybe compare thoughts with your neighbor. Parts D and E are writing integral functions. So we'll do this together, but read through them, see if you can figure out how you might be able to do that. So take a couple minutes and think about the shape of this graph, the meaning of this rate function. And just remembering how accumulation works. Remind me later. How did it go away? Darn it. Lost it. So close to the bottom here. There we go. Oh, this is all malaligned now. So at about what time, minutes into this running the faucet, at about what time does the tub have the most water in it? Around 4 minutes? Yeah, so make sure when you're looking at this, like, oh, the graph is higher to the left. This isn't a graph of how much water there is. Make sure you pay attention to the units. This is a graph of the rate of change of the amount of water in the tub. So kind of like we had bird questions and plane questions and things where we're looking at graphs of rates of change that have a variety of values. But this one starts at 2, meaning 2 gallons per minute at time t equals 0. It's a positive 2, meaning at time 0, the amount of water in the tub is increasing at a rate of about 2 gallons per minute. It doesn't stay that way for a whole minute. It's decreasing. Not the amount of water in the tub is decreasing, but the rate at which the amount of water is increasing is decreasing. It's increasing by 2 gallons per minute, and then by 1 gallon per minute, by half a gallon per minute. By the time we're at 4, when we're right around here, our rate is changing from something positive to something negative. Meaning instead of increasing, but just not very quickly, the volume is decreasing not very quickly. All of a sudden, once we pass this x-intercept there. So between time 0 and 4.2, whatever that is, the amount of water in the tub is increasing that whole time. It's increasing more and more slowly, like maybe running the water, the drain is starting to clear, or maybe you turn the faucet down, who knows. But at this point, the amount of water in the tub is actually starting to decrease. So it must be draining, and or you turned off the faucet, but, well, at least could be and, couldn't be just or. But during this last few seconds, minutes rather, during these last few minutes, there's a negative rate of change of the volume of water in the tub. Meaning the number of, like by here, at 6, I'm at like about -0.5. At time 6 minutes, the water's draining at a rate of about 1/2 gallon per minute, as in -1/2 gallon per minute increase, if you want to say it in terms of math instead of English. And then it becomes more negative, this rate does. So at what time does the tub have the most water in it? I don't know how much there was to start with, but during the first 4-point-something seconds, the amount of water in the tub was increasing. And then it started to decrease afterward, but it didn't get a chance to decrease very much. So here's where the maximal amount of water was. At what time does the tub have the least water in it? Yeah, probably time 0. Based on this picture, the y-axis is scaled the same above and below the x-axis. We spent a lot more time with high positive rates than we spent with negative rates. So there's a lot more time over which there's 4-point-something seconds of accumulating water, and it was accumulating even up to a rate of 2 gallons per minute, although it dropped from that. We were decreasing later, but not enough to have compensated. Just visually thinking about this, I had some negative rates, but they weren't very negative. They didn't even get as much as -1 gallon per minute, and that only took place over 2.5, 2 3/4 minutes, as opposed to the increase that happened at higher rates for over 4 minutes. So just on the whole, visually you can maybe see that there's more above than there is below. So there's more time when we had water going in or volume increasing than volume decreasing. So at time 0, we've got less water than we do at time 7, because 7 is pretty soon after the maximum. So B and C kind of go together. In order to answer C, you probably thought about it already in B. Now, in terms of writing integral functions, now let me move this guy to someplace more convenient for this. So if I want to write an integral function that gives the exact accumulated change in volume between the time when the faucet was turned on, time 0, and some other time t minutes later, That means I want to write a function, an exact accumulation function at t minutes later. So t is supposed to be the independent variable here. So I'm not going to use t in my integral, just on it. So I want to know what happens between time 0 and time t. And it's based on knowing our rate function. And the rate function's all written out here. R sub v of t. I don't want to put more t's in here. I could either write the function notation, or I'll just write it with the exact expression here, 0.03, but pick anything other than t, because t already has a meaning. It's the end of my accumulation, so I don't want to use it as the independent variable of my rate function also. So I'll just use, I don't know, w. Pick your favorite letter, doesn't really matter. It's not going to be a part of the answer, it's just a placeholder for, well, I'm going to let w vary from 0 to t. I have to have something other than t. Let's see, so minus 0.6t plus 2. And that looks like t squared, but that's a plus 2. That's just the rest of this function. So you could also write, oops, don't want to write that. 0.6w, sorry, plus 2. I need one more thing to finish this expression, because right now it's missing something. What else do I need? Yeah, dw, because I have to let w vary a little bit between, I'm going to let w take on all the values from 0 through t, and this is my rate function. I need to use my rate function for a little bit, not just add up values of my rate function. I'm adding up the product of my rate, that m, and, well, dw, I just picked the letter that went with it, but this is like our m times dx. We're adding up infinitely many of those. Yeah?
Does it matter which variable you switch? Because I changed the t in the integral. I wrote x and I put t in the equation. Does that matter?
In general, no, but for this particular question, I want to have a function where t is the independent variable. So t needs to be the outside part. And so we need to have something else in here. But if you're writing it on your own, you could use whatever letters you want and say that x is the number of minutes that have gone by. But since this one specified that t was the number of minutes since the faucet was turned on, then I need to have a different inside variable, a different dummy variable that takes on all the values from 0 through t. So again, this is an integral function. This isn't a specific value. If I substituted in a value for t, I could pop it in GC and get an answer for it. We will talk about how to get answers manually, because this one isn't actually even too awful of one to do by hand, but just not now. We have another few weeks of doing things the other way around first, before we can get back to this. Let's see, write an integral function v that gives the exact total volume in the water at a time t minutes after the faucet was turned on. So function v at t minutes. It's very similar to a, so I'm just going to write it in terms of a here. What's the only other thing that I need? And I didn't read this part of the directions out loud. Plus 2.5, right. The tub started with 2.5 gallons of water in it at this point in time. So at this point in time, there were 2.5 gallons of water in the tub, and it was increasing by 2 gallons per minute. So the total volume is not just what happens due to the rate, but 2.5 gallons plus what happens due to the rate. So for space purposes, I'm just going to write a sub v of t. But a sub v of t is all that stuff up there. So the difference between the net accumulation and the total amount or total accumulation function is just that initial value. It's just a single number, which if you don't know it, you can't write the total accumulation. It could be 0 in other cases. This could have been an empty tub to start with, in which case the thing I have a star by would serve as both net and total accumulation if you start from 0. 0 volume, 0 output. All right, so clear all this off. Questions? This is just writing. We still haven't talked about how to compute these. GC can compute them if you can write them properly, which is nice. And this is a heck of a lot easier to write than the approximate sums. But we can see that those are also similar. So this function up top, which is generic, first of all, it's got a function inside a function. It's a composition of functions to some extent. It's an exact accumulation of function f if f accumulates at rate r. But aside from the fact that it's kind of a composition of functions, comparing it with this g, h, and c down below, it expresses what we mean if you know how to read the symbols, but it's not quite as easy to do. So this expression here, this actually indicates that I'm adding up infinitely many things. That's not a pleasant thing to be told to do. Now add up infinitely many things. Evaluate the function infinitely many times, do infinitely many multiplications, and then add all your results together. Well, that's not really possible, but this expression tells us what needs to get done. These, now sine of 3x, that's not necessarily easy to do, but it's built into a calculator. If you put in a value for x, any calculator with like trig buttons on it can do that. If you pick the right values, you know what the values are. Or this is easier. Square some things, add and subtract. It's got elementary operations. Even this one has exponential. You wouldn't want to do this without a calculator, but this is just this unpleasant number, 2.7 something raised to the 10 times something power. So a lot of these are unpleasant, but none of them involve infinitely many things to do. They're all just less pleasant, or you could look it up in tables or grab a calculator and do it. This is telling us to do infinitely many things with this notation. Now, as I said, there are actually, we'll talk about how to, in general, resolve these integrals, how to get closed form functions, things that look more like elementary operations. Just plug in some numbers and add and subtract and use some exponents and whatever. We'll talk about how to do that. But something like this where it expresses what's going on but isn't really easy to do it, because it looks nice and short, but there's not a button to push that just says, do this. Well, GC has one. Graphing calculators have some built in if you put in enough numbers. But this x here is something that would have to be a number for GC or your calculator to give you a value for it. If you want to have a function that doesn't look like, well, how do I swirly s it? You know, how do I do this? Well, we're going to need to learn how to rewrite them in forms that look more like the expressions on the bottom. The one on the top then is called an open form function. It describes what's going on. It describes the process that we go through by using symbols to indicate what's happening, but it's not necessarily something easily computable. And in fact, in some cases, not every integral is something that can be resolved with just elementary operations. Lots of things need to only ever be approximated, strangely enough, with other functions that are close. So it's a kind of conceptual notation to indicate what has to happen, even if we can't really do those things in a finite amount of time. On the other hand, closed form functions of the variety we saw before involve not necessarily easy to do, but they're just operations that we know the relationship. So, okay, sine, I can think about ratios of opposites and adjacents and triangles, or radii and arc lengths and stuff like that from circles. There's ways to imagine what these meanings are that are just, oh, it's not a number I know off the top of my head, but I can visualize what this number answer is. Or imagine the shape of a sine function by just saying g of x equals sine of x. Like, okay, it goes like this. Period is 2 pi, etc. Whether it's polynomials, trigonometric stuff, exponential, logarithms, whatever we've got something that's computable for any value of x, doesn't involve infinitely many operations, just might involve some that use irrational numbers or non-simple numbers. Like square roots, or could be e to a decimal power, all sorts of unpleasant things, but not infinitely many steps. So they're kind of practical to have, and our goal, and this is something that's going to take us a while to get to, is to be able to take something from that open form and turn it into a closed form function. to take something like that polynomial, with a negative, it's like positive 0.3 t squared plus 2t, whatever, take that after an integral sign and turn it into something that doesn't have that integral sign anymore. Because although I know what that integral sign means, I want to know what it does. Like, what does this do to every x? How do I express this in terms of other functions that we already know a lot about? So it takes a while to get there. And so what we're going to end up doing between now and then is thinking about how do we figure out from the other way around? If I knew how much I had as a nice closed form function, how do I match that up with a rate? Because the algebra to that half of the problem is actually a heck of a lot easier. In fact, we already did a little bit of it when we were talking about Usain Bolt. We had a graph of how far he was from the starting line at measured in meters after any number of seconds up through 9 point whatever seconds it was. And we could estimate his speed as a number. If we had that formula all written out, we could even estimate his speed as a formula, because finding speed, in his case, or in general, rate of change, is just a matter of a slope computation. And I can do slope computations in general pretty easily. We're going to start working with simpler examples of slope computations in general on Thursday at the start of class, but we're going to start from just some simple looking functions. How would I express slope between 2 points, and imagine that those points are extremely close together? The algebra of resolving that extremely close together points slope issue is a lot less messy than the extremely many, extremely small intervals problem. But if you can imagine this, if I know an accumulation, I can find the rate that goes with that. If I can figure out, if I see that rate again, I know what accumulation it goes to. More or less, just different by possibly the starting value, that initial value. But there's nice patterns, because math is full of patterns. There's nice patterns for if I have polynomials, what's going to happen when I try to find their rate of change. So that when I see a rate of change that's a polynomial, I can say, oh, this is related to that other polynomial. It's easier to see going back and forth the other direction. So we can figure out quickly how to find a rate of change using some algebra patterns. And then when we see the end result, be able to look at and know what it came from. That's the process we're going to have to go through to be able to resolve functions that look like this, to write them without integrals. We're going to have to know what rate function, like this rate function, what it came from having experience in working the other direction. Because I don't know how to add up infinitely many things, but I do know how to simplify fractions. So simplifying a fraction that was an average rate of change computation or a slope computation is something that is a lot less hard than adding up infinitely many things. So we're going to work at it from that direction algebra-wise, so that we'll be able to go back and forth between rates and accumulation, back and forth, whatever direction we need to go. All right, but I'll stop with that for today. I'm going to post an assignment that's going to involve that list of 6 accumulation function possibly things to look at, as well as some reading to do from chapter 5, I believe it is. No, 6. It's chapter 6.